In this video, I'm going to introduce you to one of the major applications of calculus, at least for this course, for this unit, which is kinematics. Now, kinematics is just a fancy way of saying studying the motion of particles. Okay, so what we're looking at in this case, or at least for this course, is just particles moving in straight lines. So clearly it gets a lot more complicated than this, but for our level, we're just looking at straight lines. So typically what you have is a straight line, like this. We have an origin, which we call O, and you have a particle that is moving in some fashion. Now, it might just be moving away from the origin, or it might move and then turn around and come back, and then turn around and come back again. It depends on the function itself. We define to the right as positive displacement, and to the left as negative displacement. So if you had a little particle here, and it was sort of travelling this way, it might go there, and then turn around and come back, something like that. It depends on the function. So this is what you're looking at. So this is how you need to picture it in your mind. Also sometimes known as rectilinear motion. Okay, so first thing we need to do is get some terminology cleared up. Now, those of you studying physics will or should already be familiar with the difference between distance and displacement. Okay, we often use them interchangeably, but they do actually mean two separate things. So distance is how far a particle has travelled over a given period of time. So it's magnitude only, there is no direction, so it's always positive. There's no such thing as positive and negative. Whereas displacement is where the particle ends up relative to its starting position. So it has magnitude and direction. So what that means is if you are to the left of where you started, you'll have a negative displacement, whereas if you're to the right of where you started, you'll have a positive displacement. So an example is this one, where if we say a particle starts at A, and it travels all the way up to here to C, and then at C it turns around and it comes back to B. Now for this, we'd say the distance was the distance from A to C, which is 9 meters, going that way, and then it comes back, and that's 1 meter going this way. So the distance is going to be 9 plus 1, 10 meters, whereas the displacement is just the difference from A to B. So from here to here, and that's only 8 meters. Okay, so the displacement is 8 meters, and it's positive. We don't need to put positive, but it is positive because B is to the right of A, so the displacement is positive. Okay, so you need to be quite clear about that, because if the question asks for distance, it means this, how far has the particle travelled. If it asks for displacement, it's talking about relative position. And you need to make sure that you've got the right thing, because they can be very different. Okay, so let's dive straight in and have a look at an example. I'm going to do the first one, and then I'm going to get you to pause the video and do the second one, and then I'll show you the answer to the second one. Okay, so what we've got is a function, so we'll just concentrate on this one for the moment. We want to know the displacement when t equals 2, the displacement when t equals 8, when is it at rest, so stationary point, what is the distance travelled from 2 to 8, and what is the distance travelled in the third second. Okay, so let's have a look at the first one. So the first one's pretty straightforward. You're just finding x2. Now this is easiest to do on your class pad because you can define this variable and this makes it easy. So oops, it's just 20x, take x squared plus 9, and then we do our define that as function. Okay, cool. And then we can do f of 2, and that just gives me 45. And I know I want f of 8, which is the other one, which is 105. Okay, so x at 2 was 45, and what are we dealing with here? Meters. Okay, x at 8 was 105. When is it stationary? Okay, so that what we're now looking at is what is the velocity function, which is the derivative. So that's going to be 20 minus 2t. Okay, and we want to know when is that stationary. Now clearly that's going to be when t equals, so stationary point when t equals 10. Alright, you could also have a look at this on here by saying, well, let's plug this in. And if you get some sort of strange scale there, you can, whoops, that's not what I want to do. You can go auto, and it'll give you a bit of a better idea, but we probably still need to change that a bit. Let's make that 100, say 20, 30, and let's go up to about 30 over here. That's a bit better. Okay, so what we're looking for is the stationary point, so what's the maximum? Max. Alright, so you can see that occurs at 10 and 109, so that's our stationary point, 10. Now, the question said the distance that it's travelled between 2 and 8, so clearly between 2 and 8 it's getting, at 2 it's over here, it's 45, at 8 it's 105, and it's just getting further away. So there's nothing has happened in there, it hasn't turned around and come back, so it's just getting further and further away from the origin, it doesn't turn around until it gets to t equals 10. Okay, so the distance travelled from 2 to 8 is just 105, so between t is between 2 and 8, the distance is 105 minus 45, which gives you 60 metres. Now you need to be really careful with this, because if it had said, or say between 2 and 12, you would need to think, well, it's come out here, but it's gone all the way out to 109, so it's come from 45 out to 109, and then it's come back. So you need to work out, well, what is the difference between 45 and 109, and then how far has it travelled coming back the other way? So you couldn't just find what is it, the displacement from the origin there, and then subtract that from that, because that would give you displacement but not distance. And the question asked for distance. So the trick here is always to check where your turning points are, where your stationary points, are they within the time period or the domain that you've been given, because if the particle turns around within there, you need to take that into account. So that's something you need to be really careful of. Now, distance travelled in the third second. Okay, this often confuses students because they're not quite sure what do you mean by the third second. So if you consider t0 to 1 is the first second. Oops, first second. t1 to 2 is the second second. t2 to 3 is the third second. Okay, so in the third second it's saying, well, how far has it travelled between x3, so x at 3, and x when t equals 2. So between x when t equals 3 and x when t equals 2, the displacement there. Now we know the turning point doesn't occur until 10, so there's nothing sort of squiffy about that. We just need to subtract those two. And what you get is 60 minus 45, which gives you 15 metres. Okay, but again, if there was a turning point in there, you would need to be careful because it's asked for distance, not displacement. Okay, these are different, so be careful with that one. Alright, so what I want you to do now is pause the video and have a go at this one. Think very carefully about the result that you get here. When is the body at rest, and does that affect your answer here? So hit that pause button and have a go. Okay, so hopefully you've had a crack at this one now. I will run through the answers. So what you should have got is, so we're not doing this, we're just doing 17 now. So you should have got x at 2 is 8 metres. X at 8 is 20 metres. But there's a stationary point at t equals 4, which is quite clearly in there. And when t equals 4, which is x at 4 is also 4. It's 4 metres. Okay, so what that means is that at 2, the particle's 8 metres from the origin. Okay, at 8, it's 20 metres from the origin, but at 4, it's only 4 metres from the origin, so it's come down and turned around and then gone back up. Okay, so you need to take that into account. So when you're working, what is the distance travelled? So the distance travelled is going to be the difference between 8, so it's gone from 8 metres, it's come back to 4. So that's 8 minus 4, plus, and it's gone out from 4 out to 20. 20 minus 4. Okay, now obviously that gives you 4 plus 16, which gives you 20 metres. Now if you hadn't checked for that stationary point, and this question scaffolded you through it and got you to check, but sometimes it might not. In an exam you would not necessarily expect this. It might just say, what is the distance travelled from 2 to 8? And if you just worked out 2 and 8 and subtracted them, you would get 12, which is not the correct answer because the particle turns around and sort of backtracks in that time. So you need to be careful with that. Okay, the distance travelled in the third second is still quite straightforward because the third second does not include that turning point. So in the third second, and that will give you x. So x at 3 minus x at 2 is 5 minus 8. Now, it doesn't matter that it's negative 3 because it's distance, so therefore it's just 3 meters. Okay, so yeah, we're not fussed about direction because it's distance, it's only magnitude. So hopefully you got that one correct, you didn't get tricked with this little trick there with the turning point within the domain. Okay, let's talk quickly about velocity. Now we know we can find the velocity of a particle by differentiating the displacement function. So for example, this is our displacement function here, so we know that we can differentiate that to get x prime t, which is our velocity function, which is 3t squared minus 12t. Okay, so this is velocity function. Now if I plot that on the class pad, so it's a couple ways you can do this. Just clear this first. Clear that. And clear this. Okay, so let's put in our function there. X cubed takes 6x squared. Okay, and I want to differentiate that. So remember you can do that through calculation, diff, yeah, that's all fine. Now I can plot both these. So I want to plot the original function, and then I want to plot my derivative as well. And let's extend that down to about minus 35. Might go up to... Okay, cool. So the blue one is your original function. You can see out here it's only from 0, but that's what we're looking at because t is 0, obviously t is greater than 0. So we're going from here out to t is 6, and you can see that we've got a turning point here, and that corresponds to the 0 because this is our velocity function. So here we've got decreasing velocity, okay, and then turns around and it's increasing, so it's getting steeper, getting faster. And then at this point, sorry, you've got negative velocity, and at this point it's 0, and here you've got positive velocity. Okay, so this is where, this is the turning point. So remember, this is displacement from the origin, okay, and this is velocity. So you can see where those two line up. So if you can sort of get a handle on how the two functions correlate and what you're looking at. So when you look at the blue one, you're looking at actually displacement from the origin, whereas the red is your velocity. If you can interpret that, you know when velocity is 0, that's obviously got to correspond with the stationary point there. Now I'm just going to pause the video for a minute so that we don't run out of time, and we'll pick up again in part 2.